So thank you. I'm honored to be here at Stanford yet again. This title is way too cute. I couldn't resist it given my history here of speaking at this forum about the nature of time in physics. But what we're really going to talk about here is going to be a timeout-less data center, and we'll have some fun here talking about computer science more than the physics, as I have done in previous lectures. So we're really talking, and my co-presenter here is Alan Karp. We also have some team members here which are here to help us with the demonstration that we're going to do. So fingers crossed, and pray to the demo gods that this actually works. And we'll see what we do when we try to get that going. So what is this talk about? It's about cloud computing and about this paradigm shift that's going on in our industry and our society right now. Big movements to public clouds. Even the private clouds are starting to shrink, and everyone is talking about outsourcing their IT to the public cloud because it's just too difficult to manage. It's just too awkward. It's just too failure prone, and it's just too complex to manage on your own. So we see that this massive movement, which is now projected to be in the trillions of dollars over the next few years, is going to be an opportunity. It's an opportunity for everyone in computer science and an opportunity for everyone in business to be able to use this new utility in some interesting ways. But there are some taxes, and we've identified three taxes. The first one is the tax of complexity, which is things just get more difficult to manage as they get larger. The second one is the tax of fragility, which is they become more brittle as they get larger. And some would say that that's because of the first tax. And the third one is the vulnerabilities. We all know that all of the systems that we're working on, both in the back end as well as in our private machines, are hopelessly insecure. Security is an unsolved problem. It's a massive opportunity for someone who can solve it, or at least address it in some ways that provide significant mitigation of the break-ins that are happening on a daily basis now. But security is last in our list of things, because what we realize is that the kind of things that you need to do when you are recovering from a perturbation, and I'll call a perturbation, a disaster, a failure, a physical attack or a cyber attack, the thing you want to do the most is you want to recover as fast as possible, because the time to recover sets your availability equation and makes your systems much more available for everyone. So we'll talk about these three taxes today, and we believe that we have some simple ways of addressing them with some very minor protocol features that could lie in between the communications of computers inside large-scale data centers. So I noticed that on Twitter today, this afternoon, in fact, there was this quote. It was, "We are very good at building complex software systems that work 95% of the time."
Actually, we can do a little better than that. We
can go up to 98, I heard over here. Any up on 98? Of course, it doesn't matter how small that fraction is. If it's not zero, it becomes very large as we scale our systems. And that's the whole point. As systems get larger, they fail more often, and and those failures run into failures of failures, which run into cascades of failures. And one of the ways of looking at this is the kind of things we're going to talk about today, which is the usual errors of human failure and complexity. But also, this is from the Langley Formal Methods program, which basically says that the design errors are increasingly becoming the most serious culprit. Now, we think we can design something that will eliminate many of those taxes that were described on the previous slide. So we'll see if our reasoning is reasonable here, and I'm sure there's lots of smart people in the audience here who will have some excellent questions. So the key computer science problems, let me remind you, I'm going to put these all up at once. The reliable consensus problem is basically based on the general's paradox. The fact that there is no fixed number of messages which can complete the protocol and guarantee a reliable solution in an environment where messages can get lost. Okay, we all know this. This is the conventional view of the general's paradox. Very closely related to that is this indistinguishability of a failed process and a slow process and a failed link. And the fact that you can't distinguish them means that we have to take our beloved ideas of asynchronous systems and we have to reintroduce synchrony of some kind. And we normally do that by adding in a timeout, a duration. And the problem is, no matter what we set that duration to, we're always creating a race condition between marking the process at the other end of that wire as being suspect, or the acknowledgement coming back at the same time. And that is at the heart of most distributed systems problems. And of course, that also ties into the Fisher and Patterson result, the impossibility result, that says that you can't have a system succeed even with one failure. This isn't even a consensus problem yet. In an asynchronous system, if you have one failure, the system will stop. So this is why we have consensus protocols and why people like Leslie Lamport have developed or founded an entire literature and discipline around how to do consensus. So what we're going to describe to you today is a key idea. The key idea is think about liveness differently. I did promise I would talk a little bit about time, and I will. But the whole idea is, can we use the link instead to give us a new notion of liveness, instead of using the processes inside each of the nodes to be clicking away on the timestamp counter, and when it overflows a certain number, we say, okay, time out, let's go and see if that thing that I set off some time ago is complete now. This is a core issue in computer science. And let's describe the problems. The problems are the event ordering is hard. This general's problem means that if you've got three things going on here, P, Q, and R, then you can't tell an event at process R has happened before an event at process Q unless P caused R in some way. And so this word cause and causal comes up quite a lot in computer science. It also has a checkered history in physics too, but that's not something we're going to be discussing today. What we claim is that we can provide on-demand causal trees, and that when you use them in the right kind of way, you can guarantee, when they are stable, the kind of properties that you need to provide much stronger guarantees in the liveness properties of distributed algorithms. But that's not enough. When they're stable is all fine and good, but can you provide those same guarantees through failure and recovery? That's actually a much harder problem. And what we'd like to show you today, and which we hope to demonstrate, is a fundamental primitive, which is a new way of looking at solving this problem. So we're going to introduce you today to something called atomic information transfer. And this is, if you like, the moral equivalent of the compare and swap instruction inside the processes in the shared memory systems, but on the message between machines. And it will give us a property which is extremely hard to get any other way, which is exactly one's semantics. So keep that in mind. The second problem is consensus is hard. Failure detectors. The modern way to do failure detectors is statistical. It's called an unreliable failure detector. You're assuming that the path you're trying to use to get access or reach the thing you're talking to is likely to fail, so you use a statistical approach to basically try multiple paths. And that unreliable failure detector has got an entire body of literature that you can go and look at. What we think we can do is much better than that. We can go to algorithms like two-phase commit, which is a fail-stop algorithm, but it's vulnerable to coordinator failure. If you have a coordinator failure just at the wrong time, you really, there is no safety proof. And so this is well known. 25 years ago, this was discovered. And then there was this notion of, well, let's solve that problem, that blocking problem in two-phase commit with three-phase commit. And three-phase commit is considerably more complex, but at the same time, we didn't discover that the three-phase commit doesn't have a liveness proof. And so we're torn here between these safety and liveness properties in distributed systems. And we're beginning to realize now as computer scientists that you have to have both. To have a system that works, you have to have a combination of both liveness and safety. You can't have one without the other. It's meaningless. So Paxos, another very famous example of a fail-recover algorithm, where you can create a robust algorithm, but it's hard to understand and get right. Paxos is very famous for its many different variants, and it's also very famous for people not being able to understand Leslie Lamport's description of it. And I find the population of people fairly evenly distributed between those who like his first paper and those who like the Paxos-made simple paper. And I'm... and as we heard from the audience here, both of them may be wrong. It's an interesting problem, though, because what Leslie Lamport did is he led us right to the edge of a really difficult problem to reason about. And one of the questions I've been saying in previous forums about the notion of time in computer science is that the reason why we can't reason about them properly is because we don't actually understand what time is. And the physicists, of course, already know this. But we're struggling with it right now, and I'm hoping that we're going to make some progress. So we're going to say that causal trees make the rules in Paxos robust, and it makes them easier to understand and especially easier to verify. So why is there all this problem? Well, the networks are flaky. This picture comes from Carol Kingsbury's AFA blog about how to torture databases, and he does a very good job of putting a very simple system together and putting arbitrary network partitions between multiple processes and showing where the algorithms fail without even any misunderstanding about what time is. They're all running on the same machine, and they still have can have partitions which create misbehavior on these distributed algorithms. So what we find, though, is that app developers really blame the network. They say, the network, I can't communicate, there's something wrong with the network. And the argument is that the networks drop, delay, duplicate, and reorder packets. On the other hand, the network folks will say that the apps are to blame. And they will say, it's because of the end-to-end principle, which we agreed on, decades ago, is the right way to do things. And the reasoning behind this is that you have to have the failure recovery in the endpoints. The argument is there are some things that you just can't recover from unless the endpoint has all the information it needs. Therefore, there's no point in keeping any state in the intermediate switch nodes. Now, is one or the other correct? Our view is this. Our view is that both of them are incorrect. And it's going to take a fresh view of things to provide a good solution. So what happens when you get to a point where these things are failing? You can see where I'm going with this, right? So we have these switches in between our computers, and I'm going to describe them as dreadful. And this is a wonderful acronym that Alan came up with. He's very good at these things. Dreadful means that they drop, reorder, delay, and duplicate packets. And so one of the things you could do is you could say, okay, well, there's 4 failure modes in our hazard list, and we can try and figure out how to solve them one by one. But the network people don't do that. The network people say, no, our solution to everything is drop the packet. TCP will get the hint that we're not passing things through all the way to the end. If it finds it doesn't get the acknowledges, then it will back off. That's what that's all about. But even though TCP was designed to give you in-order delivery guarantees, you don't get that when you do an application retry. All in-order guarantees are out the window if you have to do an application retry. So this causes a whole bunch of interdependent failures, things that you didn't think should be related, but end up being directly related. And so this causes, with erasure-coded systems, this causes reconstruction storms. And with distributed systems in general, on your failure detectors, it causes timeout storms. And with the big failures that happen at Amazon, you've heard probably several times now, they have these things called gossip storms, where these statistical behavior of these mechanisms we were talking about earlier, the gossip protocols, they all suddenly start to sing at the same time. And these cause cascade failures, which basically means that you've got a switch that will misbehave for a few seconds, which causes the application to misbehave for a few minutes, which causes the database to be out for 2 hours. Now, you'd say, well, okay, that can't happen very often. Well, it didn't used to happen very often, at least not more than like once a week, maybe 10 years ago. But in large data centers, these things can happen multiple times a day. And you will see them from all the different cloud vendors will have reports, if you read the root cause analysis, of things that generally end up being cascade failures. And often it's because there are 2 failure modes in the system that are only exposed under certain conditions. But in a large enough system, anything that can go wrong will. And so we have to, the solution that we think we have to come up with to be able to address this problem is to simplify. So all of these companies have had reports in the last few months and last year or so where they've had major failures, major catastrophes that have put their systems out for multiple hours. Some of their outages have cost hundreds of millions of dollars. The Delta one in particular was $150 million, for example. And all of these vendors are constantly faced with the problem that these cascade failures will lead to this large-scale misbehavior or instability of their systems. We're no longer dealing with something that any single human mind can understand anymore. So therefore, we have to go to a higher level of technical understanding or science to be able to say, how do we understand and deal with these things at large scale? It takes a different way of thinking about things. So let me take you out of the kind of technical mode here a moment and do some historical context and describe a big idea that was the World Wide Web. The World Wide Web is a very large, was originally, the ARPANET. And what happened was we found that Tim Berners-Lee came along and he had some nice ideas. In fact, he had a great idea, which was just two simple sets of rules. And those simple sets of rules were a document language, which was HTML, and a connection protocol, which was HTTP. Simple rules, neighbors talking to each other, at least within this IP space. And what that did is it created these one-way links. And this revolution that happened with these one-way links was we could navigate from link to link to link to link, and we could go wandering around the internet on this World Wide Web, which is where we are today. Wonderful thinking of things from first principles about how we can basically manage things. These one-way links, I want you to keep in mind because they're asymmetric. There's a tail on the arrow and there's a head on the arrow. So what this allowed us to do is it allowed mere mortals to be able to get their computers to talk to each other. And that was really quite amazing. Ordinary human beings, your sister, your mother, your children, everyone could use a computer now to be able to find things out. Then there was a second harvest, and we're living this right now. And the second harvest we call cloud computing. Cloud computing is outsourcing your IT. And it's so successful that the entire industry is moving in that direction as like an almost unstoppable juggernaut. And it's a good thing because the economies of scale that you can get in large mega data centers is really quite excellent. And you also, because there's a shortage of human expertise to be able to run these systems, especially security experts, Gartner has predicted that by 2019, there will be 1 to 2 million unfilled security engineer positions for data centers because it is such an administratively intensive operation. Big opportunity here if we can address that. So that's what cloud computing is. We decided to shamelessly steal the thought process that Tim Berners-Lee had for thinking about how to deal with this, and we called our company Earth Computing. The tagline here is the solid ground beneath the clouds, and that's probably about as much marketing as you'll get out of me. But what we're trying to say here is that, well, what if you had two simple sets of rules, and those two simple sets of rules were a graph language, we call it the graph virtual machine language, which describes how things relate to each other, and a connection protocol. And the connection protocol we're going to describe to you is called the Earth Computing Link Protocol. Now, there's something very interesting and special what we think about links, which is what we're going to talk to you about right now. So there you go. Earth computing is the solid ground beneath the clouds. So what do we mean by solid? We mean that it's more resilient. First of all, we mean it's simpler. Number one, it's simpler. Number two, it's more resilient. And number three, it's more secure. That's what we think we can create by taking a fresh look at how we relate these machines together and how they talk to each other inside data centers. This is only a data center solution. It doesn't work across the WAN. We have some ideas on how it might do, but it's a much more difficult problem trying to get it to work over legacy protocols. But inside a data center, we can do something that you can't do anywhere else. So these distributed systems primitives, I compared at the beginning of this talk this compare and swap instruction, which is an atomic instruction that we all use inside our shared memory systems, All the processes, all the cores can talk down to the same shared memory system. And the atomic primitive there is called compare and swap. And it's led to a lot. The latest way of doing things now is called lock-free data structures, which is extensively used in all of our operating systems and all of the new work that's been done on distributed systems. But it gives us, all these concurrency libraries are now being transformed over to using these lock-free data structures, but they're all leveraging this thing called compare and swap. It's made from an atomic read, modify, write instruction. So you're reading something from memory, you're modifying it inside your processor, and you're writing it back. Or you're instructing some other machine to do that for you, or like remote DMA, for example, is an approach that's done on some networks. So this gives us the concurrent safety, it gives us the non-blocking. It turns out to finally, after 15 or 20 years of work on this by the academic community, we're starting to be able to make them perform as well as the previous locking-based systems, but much more safely. We would like to introduce the idea that what's missing is the communication messages between computers need a similar atomicity principle. Right now, we have a process that Peter Alvaro tells me is called the bang, bang, bang theory of networking, which is basically bang, I want something, and you wait for the acknowledge, and when it doesn't come back, you go bang again and say, hey, I need it now, do you still have it? And then you go bang, bang. And what happens is everyone in the data center all goes bang, 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 bang at the same time when the network gets congested. So now you're starting to see why these cascade failures start to happen and what we're trying to do about it. So we believe that these atomic information transfer, the key idea essentially is let's create a recoverable token that can be sent, and if the operation that we want the process on the other side to do doesn't succeed, it sends us the token back. It's a mechanism for doing this atomicity in messages, which allows us an opportunity for doing recovery in a much better way. So there you go, deterministic in-order delivery. When you ask for it, it's a reversible token, which says I can send it, and sometimes I can send more than one, but there's a small number, a very small number. It's only a small amount of rollback that you can do with these things. And it creates this process of a reversible atomic mechanism. So deterministic recoverability, and it's durable. If a system fails, if a link fails, we can still recover those tokens. That's the way it's designed. Now, there's one of the things that we have thought about in the way that we're going to show you the networks here, and that is that typically computers are much less reliable than switches and routers. And the reason for that is because the software crashes. Switches, have got some pretty hard core firmware in them and mostly hardware. So when they're doing things at very high speed, you can push them to the limits and they don't fall over. Whereas that's not quite so true of our operating systems today, most of the time. So the while operation is the normal way you would do this with a shared memory system. The equivalent would be, for AIT, would be a similar kind of line that you would have in your code. In other words, we're saying that you can't build robust systems without both of these primitives. And once you realize that you need both, then you start to realize that you can do recoverability in ways that wasn't possible before. And this is necessary as we're building systems very large. So we've timed this presentation to be about 45 minutes, and that's including the demo. We have plenty of time at the end for questions on camera, and there are certain questions that I would reserve the right to not answer on camera because there's a proprietary nature to some of the things that we're doing, although we don't mind sharing it to people who are academically interested in what we're doing. So typically the way a data center is constructed is you have a whole bunch of servers, and then above the servers you have this multi-level close network which is used for the shared interconnections between these machines. Now this was all well and good when most of our traffic was going north to south, up to the internet and down to the servers. But these days in most modern data centers, most of the traffic is actually east-west. So those computers at the bottom, those servers, actually want to talk laterally with each other, a lot more than they want to talk up. But they're forced to go up, sometimes 3 hops up and then 3 hops down, in order to be able to talk to a server that might be in the adjacent rack to them, for example. What we've done is said, well, what if we had a system that didn't have any switches? What if we did our own routing? People have tried this many, many times before, and we think we understand why they haven't succeeded. we think that we can build a system that will be more successful in building distributed algorithms on top of than the current system with shared network switches, which will drop, delay, duplicate, and reorder packets. So that's basically the claim. So what we have on the right-hand side here is just rows of servers, racks in a data center. And notice that there's some links missing here, and there's some nodes missing. That's because that's how it is in a real data center. Real data centers are never a perfect, mesh of anything. You can't build a Cartesian coordinate addressing system on this and expect it to work, because these things fail in the middle. So what we do instead is we build spanning trees on every single node. We discover what wiring is already in there, and Alan will show you how that works in a moment, which means that not only when you first bring these systems up can you discover what's actually there, you can also adapt as you go along as things are failing and adjusting and growing as the data center grows. How does it compare to the way that people do things today? Today, people have a firewall at the edge of the data center. We all know that that doesn't work because all of the attacks come from inside the data center today. Typically applications escalating to the operating system, they will turn on the NIC into promiscuous mode, and they'll send a few well-placed poison packets out to the switch, and the switch will then start to sing. And then you get to be able to see who's talking to who, and then hop over to another system, and basically intrusion these days is basically a graph problem, and all the attackers think in graphs. This is a well-known Twitter statement. All attackers think in graphs, the defenders think in lists. As long as the attackers think in graphs, they will win. So what we're doing is saying, let's do something different here. Let's have these nodes and links that connect to each other, which is the picture on the right-hand side. But we're able to use algorithms that divide up these systems instead of having human hands on keyboards editing ACLs. And if you can have an algorithm that can move these boundaries between the orange and the blue and the yellow tenants, then what happens is you can make them dynamic. You can make them grow and shrink over the day as you want to use things for different purposes. You can make them adapt when you have a DDoS attack, for example. But the thing to remember here is that we can build into this system a thing that Whit Diffie said sitting here a few months ago. He said the problem of security is confinement. It was solved in the 1970s. And the difficulty is that we've tried to leverage cryptography ever since to try and assume that we can get confinement from that. And all we've done is we've created this explosion of complexity in key management. So what if we could actually get confinement? In other words, hardware-enforced confinement of packets to the areas that we want here. And what we're describing here today is just the basic protocol primitive that allows us to manage a single link in a much more intelligent way than we've done before. So let's draw a bigger picture here. What we're doing is taking the whole data center, the big blue thing that you can see, and we're fitting a smaller number of computers inside of that, which are directly connected to each other. In other words, these machines are connected one up, one down, one left, one right, and across the corners if you want. In other words, they're talking to their neighbors with short cables. We can start small. We can start just in half a rack inside a customer's environment that wants to say, I want to run some Paxos systems inside here that are really super reliable. Can I do that? And then they realize that that works really well, and they give us a couple of racks. And then they give us half a dozen racks. And then a year later, they give us half a row. And then 3 years later, we're taking up the entire row in the data center. In other words, you can try this out in the small and see if it works. You can start to expand it into the production environments as you're finding it useful. And we think that that's going to be a valuable thing to do. So keep in mind that the Earth core here is made up of two kinds of cells. We call them cells. These are just compute, storage, networking, packet handling. The red ones connect to the outside world, so obviously they have to be bridges of some kind, or membranes to keep out the bad stuff from the outside. And the dark red stuff is not connected to the outside at all. You cannot express their endpoint. You can't express an address that can talk to them from outside. And this is true both from the outside to the inside, as well as from one cluster of tenants to another cluster of tenants. They literally are as if that they've been physically severed from their cables. Let's take away all the complexity here and just simplify this right down to what are we talking about here? These individual nodes, which we're making this hexagon shape here to imply only one thing, and that is that there is a finite number of ports on these things. It's more than you normally have on a server, which is like 3 or 4, but it's a lot less than you would have on a switch. It turns out that what the magic is that we've discovered, this Goldilocks zone of how many ports that you need, is in the range of, guess, 7 plus or minus 2, a very famous number. But it turns out that some very interesting things happen when you have that number of ports. It forces you to use multi-hop behavior, which in general in networking you think is a bad idea, but it turns out to be a really good idea when you're trying to build self-organizing systems. Now, those are the cells. There's a cell agent in the middle. It might be an actor system, for example. But the NICs, the network interface controllers, the fan out from those and have connectors on them. But the really interesting aspect of this is those blue things. We have taken the NICs and the cable between them when we plug them together, and we've made that link a first-class object. And that means that we can put things on them that will be remembered when the link breaks. In fact, the protocols that we use keep complementary information on both ends. And we'll give you some use cases after we've shown you how we're working with this. Now, where we're leading to with this. So between any two cells, I can have this private bipartite relationship. And that bipartite relationship is extremely important to the theory behind how these protocols work. You have to be able to exchange conserved quantities between these two links. But because you can do that on a link-by-link basis, you can compose these over multiple links. Now, I'll give you a heads up as to how that might look. Now, let me go back here 1 second here. Why would you want to do this? You would want to do this because you could basically replace timeouts. You can replace heartbeats. You can create, I'm going to call it a temporal intimacy or a presence management between each of these nodes, or between a set of nodes in something like a tree, in a way that you can't do any other way, allowing you to eliminate heartbeats and timeouts. So where is this going? There is a very fundamental problem. Moses and Halpern won the ACM prize for something called common knowledge. And many of you are probably very familiar with that paper. And so what we've done is we've kind of figured out how to circumvent the common knowledge problem. So keep that in mind as we go through this, and we're totally open to questions and answers afterwards. But let me just put something in your mind here. If I'm going to compose this presence management across multiple of these nodes, then this is the picture that I find most people kind of get it. They understand it when I show them this. And it say, okay, well, that's a nice toy, but what happens, with a real system? Whoops, sorry. Oh, it's not working.
Keep hitting the button again.
I did. It went on. All right. So it's that's very interesting. Now. That should go to... I'm going to show you this later after Alan's done the presentation. All right. Right, now it's working. All right, good, finally. Oh, I see what's going on. I can't see it here. My local display is showing it. So, give you a kind of a feel for what's going on here. We are ignoring time. In fact, we're really thinking about time in a totally different way than most people do. But you can see here that if I start with an application over here that talks to its network asset layer down here and says, please guarantee that this thing gets over to this thing over here, and then it gets taken off. That the thing that's going on in the middle is a kind of temporal intimacy which is much, much stronger than we're normally used to having in a bang, bang, bang networking environment where we have to use timeouts. So it's one way of thinking about it. So I'd like to move on to the demo and introduce Atsushi, who is going to be on the keyboard here, and then hand over to Alan to describe what we're doing.
So I don't know if you guys know this, but Paul is the bravest computer scientist in the world. He once gave a talk on a paper by Leslie Lamport, with Leslie Lamport in the audience. That's a very brave computer scientist. I am not brave, but I am foolhardy. and I am going to attempt to give you a live demo while being taped for the internet. So, so what we have here, they don't let me touch equipment. So Atsushi's going to do all of them. What we have here is Marge and Homer, and they're connected through a switch, and they're happily pinging each other. All right? Now, what I'm going to do is I am going to disconnect Marge, and after a few seconds, she's going to realize that something's gone wrong. You can see up there that something's gone wrong. Homer, on the other hand, doesn't know about it. He's talking to the switch. He's still connected to the switch. And he's sending his packets to the switch. Now, the switch is desperately trying to find a route to Marge, which means in a real network, it's spewing out packets all over the place, taking up bandwidth that could be used for useful work. And finally, Homer, this is actually about 45 seconds, figured out that something's gone wrong. We can plug them back in. And then they will start pinging each other again quite happily. This is the problem in big networks, is we have timeouts that we have to deal with. So if the switch is the problem, what if I connected them directly? Okay? So I connect them directly, and now you can see that they are happily pinging each other. And when I disconnect the link, it takes a few seconds. It's still a timeout. Of course, the network protocol doesn't know that there's no switch. There might be a switch. But also the recovery process is so onerous that it's worth waiting a few seconds just to see if maybe it gets fixed. So that's the way things work in a conventional network. How do things work in ours? So we're going to bring up a display. We've got 4 ports on each machine that are running our protocol. And we're going to have a display that's going to show the activity on those ports. And of course, we got an error dialog. It's not just Windows that does that. There's Marge, and there's her display. See, I cause trouble even when I stand close to equipment. I don't even have to touch it to cause trouble. All right. So with each of the 4 ports, and what I'm going to do is I'm going to plug this orange cable into some port. Now, with TCP, you have to be careful which port because, of course, the address depends on the port. But with our protocol, it doesn't matter, which is a good thing because I'm kind of careless. And once I plug it in, what you're going to see is as soon as the lights come on the NICs, these things become alive, and you can see. Now, because this is a private link, I'm not wasting any bandwidth by using it. So rather than use timeouts, what we're doing is we're pushing packets anonymous packets back and forth as fast as we possibly can, right, to make sure the link is alive. So those are event-driven. You get an event, you know the link's alive. You get an event, you know the link is alive. And when I unplug it, it turns out that every NIC card in the world, every NIC in the world, when you unplug the cable, raises an event to the OS. But the OSs don't use it because they assume they're working through switches, and what would be the point? But what we do when I unplug it, it stops immediately. But it also notice on the numbers up there, this is just the last 3 digits of a count of numbers. We're sending, 25,000 a second or something like that. But you'll notice that they're off by exactly 1. That's a miracle. If you're doing recovery from a distributed system failure, knowing that you're off by exactly 1 is a big deal. So here we go again. I will unplug, and they're off by exactly 1. Okay? That's wonderful. And you have another red cable?
You want to show AIT?
And we're going to, show we can do this again. And then we're going to send an actual message. So right now we're just sending these anonymous packets. I think Homer would like Marge to buy some beer. So he's going to tell her to buy beer. He's going to tell her to buy beer. Okay. And or beef, either one.
It's okay, we'll get it.
Yeah. Mm-hmm. And he's going to send it on one of the active ports, and there it showed up. Now, on Marge, Marge is going to tell Homer she's actually going to buy bread, but what she's going to do is send it on one of the inactive ports. Okay. Oops. Maybe you want to sit around over here. We actually rehearsed this, and none of this crap happened. I want you to know that. Yeah.
There's definitely a demo DOT. It's definitely not,
Okay. And she's going to send it on, let's say, the second one, non-connected. And of course, nothing happens. But what happens if I disconnect this cable and plug it in, it's going to show up on the corresponding port on the other side. Okay? So we don't lose these AIT tokens. You don't lose them. They are there. Now, being off by exactly one is a very good thing for recovery, but there's one thing missing. And that's something we call tick-tick-tick. The I know that you know that I know property. So if I'm connected to you over one of these cables and the link breaks, I know it broke. I know that you know it broke. And most importantly, I know that you know that I know it broke. Because what that means is we now both know to hold on to the state we need to reestablish the message and all the ordering guarantees that go with it, right? Without having to exchange the message, which is the generalist problem. So that's the essence of the link protocol we're using and the interesting properties that we get. Now it's back to Paul.
Okay, thank you, Alan. So this problem of knowing what's going on the other side of a broken link, sounds like an impossible problem, right? It says, but if both sides know that it broke, both sides know what to do next. And that is, that is kind of interesting because we're going to talk about the two generals problem briefly here, but I found this wonderful picture on the internet where a computer scientist told his daughter about this problem called the generals problem. And so she drew this picture and she said, "Daddy, I found the solution to the two generals problem." You dig a tunnel. And kind of, what we do is that tunnel that goes underneath is kind of a symbolic idea of how this can work. But what we're really doing here is we're changing the assumptions behind the common knowledge problem. Or if you wanted to call it a general's problem, it's the courier can be seen by both sides now. So if the courier was a pigeon, we can both see that it got lost and wandered off. Or if the courier was on horseback, we can both see that they got captured. And so the fact that both sides can see the courier is the change in the assumptions that we're able to make in these distributed systems algorithms. Now, what are the use case for these things? Well, two-phase commit. If you can give this protocol to a two-phase commit protocol, you can end up with both a safety and a liveness guarantee. And with Paxos, instead of having to have long convergence times for things that go wrong with Paxos because of the cascade failures, by the way, the problem with most consensus algorithms is that they make an assumption that each packet fails independently. In other words, the RAFT protocol in particular that Diego Ongaro has developed here at Stanford has a wonderful demonstration, and it's used extensively by the systems out there, but the assumption that each packet fails independently turns out to be problematic, because what happens is when you're going through a switch network, the switch fails all of the packets at the same time. And so these single points of failure that cause massive, disruption end up causing multiple elections to be kicked off at the same time. And then another example of distributed protocols is routing. A binary link reversal protocol, which is used fairly extensively in wireless systems and in some wired systems, has this property that it has an arrow. That in the DAG, it has the tail of the arrow and it has the head of the arrow. You need to know if that's being swapped atomically. And if you can guarantee with your protocol that that's been swapped atomically, that all of a sudden now you've got much stronger guarantees in being able to do failovers much more rapidly and much more certainly inside the systems. So this common knowledge problem goes from all the way from, nobody knows anything about anything, all the way up through this hierarchy, up to everybody knows everything about everything. But the original paper on this actually boiled the problem down to a simultaneity problem. You cannot simultaneously know the knowledge on all of the places. And that really goes straight back to relativity, to special relativity in particular. So the fact that simultaneity is a myth, you really can't have it, is the underlying physics of what we're dealing with in this universe. And the common knowledge problem simply reflects that. So what we're able to do once we have this protocol is to do even more interesting things. We've got an agent in here, which may be an actor, the network interface controller. The blue area is where we create this deep asynchronous domain, where we're doing this game with unobservable presence management between the cells. And what we can do is we can now do interesting things on top of that, starting with the AIT token, which can then have a payload and say, please make sure this gets delivered to my friend or this set of friends that I want to make sure gets it. So you can do things like atomic broadcast that you can't do any other way, or at least not reliably. So you could put all this functionality into a NIC. You could put it all in the software. In fact, the demo that you're seeing here is a modified device driver. We're actually doing it in the interrupt service routine itself. So we're really truly event-driven. And if you think through the protocol implications of what we've done, building a protocol that doesn't require any durations of any kind is really quite new. It's very novel. We haven't seen that done by anyone else. To make that purely event-driven gives us these properties of being able to replace timeouts, replace heartbeats, and so on. But the opportunity to do more interesting things in the messages computationally, as well as complementing the things that are going on computationally inside the nodes, is, we think, a new opportunity in distributed computing. So we could, for example, build these things that we call traps, or tree graphs. This is the combination of the properties of both. But notice that we're solving the reliability problem by creating, on top of the bare metal, this network asset layer, which is a super reliable, lowest level, formally verifiable small system at the very base of this thing, which can continue to talk to all of its neighbors, even though in a virtualization environment, the operating systems and the containers and the applications on them above can crash and go away and be replaced and restarted completely independently of what's going on in the network asset layer. So there's multiple layers on here, which we've shown. The network asset layer is one of the lowest layers of this protocol. The second layer up, which is in this particular color, I think is orange, is the data asset layer. This is where we plan to do immutable systems. We plan to put the little data there, the configuration data and the boot images that you really don't want some enterprise scale ransomware person coming in and scribbling over. We can get you back to a known good state extremely quickly by the protocols at the bottom in the network asset layer, providing these guarantees in the data asset layer to make it immutable. And then that provides capabilities for the third layer up, which is the computation asset layer. From there, we can provide things like failure detectors as a service. We can provide consensus as a service. We can provide network-assisted transactions as a service. And when I say transactions, I mean fully transactionally consistent operations that can be perhaps 100 times faster than two-phase commit and perhaps 1,000 times more reliable. We think that's interesting because if you can make transactions that cheap, you can put them everywhere. And now you can build a much more reliable, much more scalable system than we have been able to before. So what I'm going to do now is switch back to Alan, and we're going to show you a demonstration on a simulator of where this system works. So,
yep, there it is. Okay. So I'm going to have to try to guess here. I can't see very well. Where's my mouse? There it is. Okay. So let's say you bought what we're selling, okay, and you're going to build your data center. And you decided you're going to build a 60-node data center in a regular grid. So you go ahead and you build it, and the first thing you see is it ain't a regular grid. Okay, there's wires misplaced, there's a wire missing. This was what Paul said. In a data center, when you build it out, 3 to 5% of the wires are going to be misplaced. Now, in a conventional system, you're going to send somebody in there with a flashlight to either go fix them or figure out where they really are. But what we do is when the system comes up, we do what we call a discover process, which builds a spanning tree centered on each node, rooted on each node. So I'm going to click on a node here, and you're going to see that there's a spanning tree. And in the process of doing that building of the spanning trees, we're going to figure out what the wiring actually is. So there's nobody with a flashlight going in to see what's going on. We just build the spanning trees and figure out what the wiring actually is. Now, even though your data center looks pretty clean there, in 6 months, it's going to look more like this. Okay? You know that. We know that. But we still maintain the spanning trees. I click on a link, there's a spanning tree. I click on a link, there's a spanning tree. I click on a link, there's a spanning tree. But when we build the spanning trees, you see that there are links, like this one right here, that isn't in that particular tree. Well, we remember stuff about it. We record state about that link. So let's say I go to this link and I make it fail. You notice we just flipped right over because we knew information about that spare link. Now, here's a cell that doesn't have any pruned links, as we call them. It just has 2 children. What if its parent link fails? Well, it just finds a new route back around. So now you'll notice here that it could have gone this way and saved 1 hop. It picked the suboptimal path. That's because we're only using local information. We have no global information at all. That's what makes this scalable. The price we pay is sometimes a suboptimal route, but you can't make it scalable if you're going to have centralized information. And of course, if a node fails, well, that's just a bunch of broken links, and we route around that. Okay? So think about it. What we're able to do at this point is hide permanent network failures from higher levels in the stack. And it means we can enforce with the tick-tight, because of the tick-tight-tick property, we can enforce all kinds of interesting guarantees. Like if you're communicating on a tree, you have message order guarantees, because there's only one path between any pair of nodes. In fact, you can do other even higher level guarantees. Now, you could compute on trees in a switch network, but what's the point? The switches are dreadful. They're messing up all the neat properties you get by being on a tree in the first place. With this protocol, we get all those neat properties.
Thank you. All right, so what we've done is talk to you about this link protocol we've talked about, how we can compose it, and what kind of use cases that we have that we could take it to. We think that there's some interest here for the academic community, and we think there's tremendous interest here for the commercial industry that wants to build more scalable data centers or data centers of any scale.